Ma'am, shall I start the session?
Yes.
Okay, great. So, good morning, everyone, and welcome to the Mastering Up International Conference Series 2025 to 2026. Today's theme is International Conference on Cryptography and Mathematical Security, and super exciting stuff ahead. So, big cheers to Dr. S. Gayathri and all our amazing participants. You all rock. So, let's keep it chill, interactive, and fun, and grab your coffee or juice, and let's dive in. Ladies and gentlemen, and dear friends, a very warm welcome to all of you. It's an absolute delight to have you here for today's exciting session on post quantum cryptography securing data in the quantum era. We are here to explore a topic that's not just about technology but about the future of trust, security, and innovation in a world that's moving faster than ever. Now I know the title sounds sounds a little heavy, but don't worry. We are going to keep things engaging and practical. Think of this as a friendly conversation about how we can protect our digital lives in a time when quantum computers will be powerful enough to crack today's strongest locks. It's about being ready before the storm hits, and more importantly, about turning that challenge into an opportunity. As we dive into the session, I encourage you to stay curious, ask questions, and share your thoughts because the future of cryptography is not just for experts, it's for all of us. Remember this, the best way to predict the future is to create it. So, let's take this step together in creating a secure and quantum ready tomorrow. Before we begin Dr. Gayatri's session, I would like to take a moment to introduce about her. So, all right, everyone, I hope you are ready for some serious inspiration because today we have the absolute honor of welcoming a truly remarkable personality to our session. Please join me in giving a big cheerful welcome to Dr. S. Gayathri, Assistant Professor at SRM Institute of Science and Technology, Tamil Nadu, India. Dr. Gayathri is someone who does not just teach but inspires. With over 11 years of teaching experience and 6 years of impactful research, she has contributed extensively to the world of quantum computing, VLSI, and emerging computational technologies. Her specialization in T-count optimized quantum circuit design for floating point arithmetic might sound a bit technical at first, but it's exactly the kind of groundbreaking work that will shape the future of how we compute, secure, and innovate. So, today we are not just listening to a professor, we are learning from someone who has published in top SCI in-text journals, review for reputed international platforms, and deliver invited talks around the globe. So let's keep our minds open and our curiosity alive and our energy high because, as the saying goes, great minds don't just think, they inspire others to think even bigger. So before we dive into today's session, I would like to take just a moment to introduce you to something that's close to our hearts, TEMS Tech Solutions, a proud series venture that's changing the way we see and use technology. At TEMS, we stand by three simple but powerful values: innovation, excellence, and affordability. Whether it's cutting edge engineering or next gen scientific tools, we believe everyone should have access to transformative tech. As a visionary, um, Steve Jobs once said, innovation distinguishes between a leader and a follower, and at times we choose to lead with purpose. From digital marketing and web design to AI powered tools, server management, and mobile app development, our work spans across industries like aerospace, medical applications, energy, and more. We don't believe in one size fits all. We believe in tailored solutions that help businesses thrive in a world that's constantly evolving. As Albert Einstein wisely said, uh, strive not to be a success but rather to be of value. That's our mission, to add real value through strategy, technology, and a mindset focused on progress. But what makes us most proud is not just our business, it's our impact with our initiative Mastering Up. We are focused on empowering the next generation by equipping students, especially from rural and underrepresented areas, with real world skills for real world success. Because, as Nelson Mandela also said, education is the most powerful weapon which you can use to change the world. So today, as we begin this session, let's not just learn. Let's imagine, build, and shape a brighter tomorrow together. The future starts now. So at the end, I would like to introduce to the motto of Dr. Gayathri: empowering minds through knowledge and shaping the future with quantum innovation. So I would like to hand over the session Dr. Gayathri, and also a thanks a lot for joining us today, and over to you, ma'am.
Yes. Good morning, everyone, and thank you, madam. That was a very great introduction indeed. I never expected this kind of introduction. And thank you. And participants, good morning to one and all over here. So I would like to thank for the opportunity given by Mastering Up and their enthusiasm in creating such innovative events. Okay. So today we are going to discuss about post-quantum cryptography. How do we secure data in the quantum era? So we will discuss on what is the concept of post-quantum cryptography, what is the necessity of moving towards post-quantum from classical cryptography schemes, and categories of post-quantum algorithms that has been stated in the literature till now. Okay. So what is, before starting, we should know about this quantum computing. What do you mean by quantum computing? So right now we are working with computers. We have phones, mobile phones, we have our laptops, desktops, everything. They are all called as computers. They work on the principle of classical mechanics, wherein they are governed by the matter and energy, which is dealing with the objects at the macroscopic level. Okay, but quantum computing is quite indeed different. If you recall the statement of Moore's law, the Moore's law statement is that the number of chips fabricated, the number of transistors embedded in a chip should double every 18 to 24 months. That was his statement. But right now, if you look into the year of 2020 or 23, we are nearing the end of Moore's law because we are embedding a lot of transistors in a single integrated chip, which makes that we are right now dealing with microscopic level or subatomic level of matter instead of macroscopic level. So if we go into the depth of understanding a matter at the subatomic level, classical physics, which is deterministic in its outcome, will not support you to analyze its behavior. So we need a technology that is absolutely random, because particles at the subatomic level, they are random. So we need to, if we need to understand their behavior at subatomic level, we need to shift to the mechanism of quantum mechanics. Okay, so the basic principles of quantum mechanics includes three important principles. One is superposition, the second one is entanglement, and the other one is uncertainty theorem. I hope everyone is very known about this uncertainty theorem proposed by Heisenberg. Okay, so in the classical computers, always we refer to the basic unit of information as the bit. The bit could be either in one of the states, either a 0 state or a 1 state, like this. A classical bit has only two states to process your data, either in 0 or in 1. But in quantum computing, a single bit of data is represented as ket and bra, means your ket 0 and bra 1, which is known as a qubit. So qubit is nothing but the acronym for quantum bit. The quantum bit is also called as qubit. We should call it in short. Okay. So what is the beauty of representing this 0 and 1 in terms of ket and a bra? They are able to exist in any of the one states as well as in a linear combination of both the states. So we can process the information in terms of 0 and 1 separately, also in the linear combination of 0 and 1. So imagine, so if we represent them on a space, the qubit can be represented on a three-dimensional space. So the physical implementation of qubit, how do we implement them in physical implementation? We could implement this classical bits in physical implementation by representing the voltage value. If we have done with any of the simple experiments in ICs, we declare the voltage level for them to determine logic 1 is plus 5 volts and for logic 0 is minus 5 volts. The excitation of your voltage, okay, the excitation of electrons based on the supply voltage that you give, okay. But in quantum, so we have informations of 0 and 1 represented using this spin of an electron. Okay, if your electron is spinning up, it could be represented as ket 0. If your electron is spinning down, it could be represented as ket 1. And if your electron is spinning in both the directions simultaneously, it can be represented as 0 and 1 simultaneously. Okay, so it can be able to work with either 0, either 1 or both states simultaneously, provided they should be in the linear combination of both. And now coming to this properties of quantum systems, as I told earlier, superposition and entanglement are the important properties that is driving your quantum systems. In superposition, if two or more quantum states are added together, the resulting state would be another quantum state. For example, I have a ket 0 state and I have a ket 1 state. They are blending up with each other. So the resulting state would be the linear combination of ket 0 and 1, probably ket 0 plus ket 1 by root 2. So this state will be another valid quantum state. Okay, so you could see this animation is better displaying the property of superposition. But when does this superposition destroy its property? Whenever a person is tending to measure the state of the qubit, this superposition will not be available. The linear combination of the bits will not be available. Your measurement operator will tend to make your superposition qubits to be available in either 0 state or 1 state alone. That is what is meant. And the next important property is entanglement. Imagine a pair of particles is generated in quantum state. Okay, a pair of particles are generated. One particle is here in Earth and the other particle is far away from the Earth. If you try to measure the property or the quantum state of one particle, independently you cannot measure this particular particle which is at the Earth without the help of the particle which is far away from the Earth. Okay, so when the pair of particles are generated, the quantum state of one particle cannot be independently measured without the help of the other. But they may have dissimilar properties or anything, but measurement is not possible. Like I do remember a professor of IISc Bangalore who always says entangled pairs are like a husband and wife. They both may not resemble their characteristics, they might be opposite in their characters, but still, in taking an important decision, they both will not take without the approval of the other person. So similarly, the measurement operation cannot happen without the help of the other, even if they are far apart. Indeed, if you have to say technically, even if they are light years apart. Okay. And the next important property is, this is to be remembered when you are constructing quantum circuits indeed, the reversible property. So recall the basic logic gates like you have learned AND, OR and XOR logic gates and all. Let us take an example of XOR logic gate. We have two inputs, right? So A and B, we have two inputs. It is capable of generating a single output alone. Okay, A XOR B. When both of the inputs are similar, your output will be 0. When both of your inputs are dissimilar, your output is 1. That is the property of XOR gate. But theoretically speaking, it means that we are giving two inputs, two bits of information as inputs to the system, but it is generating only one single output. So scientists found that what happened to the one bit input that is sent as the information input. Okay, so they believe that getting one output at the end of the logic gate means that the information is erased in between, vanishing of information, and it is dissipated into the environment as heat. And they have quantified this information loss also using the mathematical formula Kt natural logarithm of 2. So K remembers your Boltzmann constant and T is at which the computation is being done, the temperature at which the computation is carried out. Okay. So quantifying this made the invention of reversible logic gates. So reversible logic gates will have equal number of inputs to the equal number of outputs, so that we will not have any information erasure during the processing. Okay. Also, they have to solve this property of having uniqueness in output. Okay. So if I have one output over here, imagine I have the inputs as A and B, A, B and C, and I have the outputs as X, Y and Z. Okay, if X, Y, Z is of a particular combination, the same combination of X, Y, Z should not repeat for any other combination of inputs for A, B and C. Means that you should preserve the uniqueness between the vector input states and the vector output states. Why it is so? Because only then it is possible for you to determine whether if you have any fault in between the computation, it is very easy for you to determine where does the fault has actually happened. So uniqueness in mapping the inputs and outputs is mentioned here. So that is what it states. Having one-to-one mapping between the input vectors and the output vectors, it will help you to reconstruct your input vector states from the output states. Okay. So this constraint should be remembered when you are focusing on designs of quantum circuits. So quantum circuits are working basically with the ideology of reversible logic gates. They have been extended, and if you have an idea of reversible logic gates and if you are working over it, you can definitely stretch your way to work with quantum circuits indeed. What is the need for quantum computing? Why do we, other current computers we have, they are evolving so much, they are very good in their performance, but why do we need it? Is there any technical necessity that we should require quantum computing? So if you classify the problems solved by a computer based on complex classes of complexity theory, over the probabilistic space we have around three classes of probability complexity theory. One is P class, and the other one is NP class, and the third one is NP complete. Okay, so we could see that P is a polynomial class of problems that is very efficiently solved by a classical computer itself. And the NP complete problems, or the problems, they are non-deterministic polynomial problems. Okay, so over the non-deterministic polynomial case, we have this intermediate stage of this bounded error quantum polynomial time, that is BQB problems. This non-deterministic polynomial and BQB problems, they both concentrate on quantum computing problems. Okay, so non-deterministic polynomial problems are the class of decision problems that are solvable in a polynomial time by a non-deterministic machine. For example, if you have to solve an n cross n Sudoku problem, a box packing problem of n cross n size, a traveling salesman problem without any definite size with a large number of nodes, okay, those can be solved by only a non-deterministic machine, totally a machine that is run with the random quantum mechanics. Okay, so in this particular case, if you have to if you have to increase your efficiency of solving NP complete problems, you have to definitely look into a non-deterministic machine. Deterministic machine like classical computers will not be a sufficient candidate for solving this. It is not a suitable candidate for solving this NP complete problems. And the next one is this bounded error quantum polynomial problems. They are the problems that are solved by a quantum computer in a polynomial time. Okay, so factoring a discrete logarithm problems. Peter Shor and Peter Shor's factoring algorithm and Groover's search algorithm or such candidates. They are coming. They are very good in solving such problems, factoring a discrete logarithm. The next one, you could see this picture. So what is the necessity? If imagine that you need to solve a maze problem of a deterministic size, a classical computer, how it will solve? It will start right from this place and it will start traveling over different combinations, n number of trials it will take to find out its destination. If the first trial is lost, it will move on to the second trial. If second trial is lost, it will move on to the third trial. So the number of times that it is trying to find out the path in the maze problem will be n number of times until it is finding a suitable solution. But imagine if the same maze problem is given to a quantum computer, how many number of trials it will take? Because of the efficient handling information capacity using qubits, which is able to process information as 0, 1 separately, also the superposition of 0 and 1, it is able to work out in all possible combinations at the same time. At the same time it is able to work, and in not n trials, in just one single trial, it will be efficient to find the destination through the correct path. Maybe like, yeah. You could see this animation, I hope. So that demonstrates the definition that I gave you. So classical computer is taking n number of trials to solve this maze problem, but quantum computer is going to take only one single trial to solve a maze problem. A simple example that is shown here. So imagine the efficient information handling capacity and the effectiveness of a quantum computer in solving a problem. Okay, and do we require, there comes an important question everywhere we go and talk about quantum computers. Do we need to go completely replace quantum computers? Sorry, completely we need to replace the classical computers using quantum computers. I think there is no necessity to replace the classical computers completely. Okay, there are certain problems that can be solved by the classical computers in a very efficient way rather than quantum computers, but depending on the problem. Okay, what type of problem that we are going to take, what kind of problem that you are going to solve, that determines whether you should use a classical computer or a quantum computer indeed. If for solving a simple problem like an 8 cross 8 chess, or a very small problem like Sudoku problems that an efficient computer can itself solve, there is no need for us to bring a huge quantum computer to sit over and do that thing. When you have an n cross n size, a large prime number or a large prime number to be factored, a very large number of grids to solve a chess, in those cases, this is definitely an efficient candidate to be taken into picture. Okay, so as I told you earlier, so quantum mechanics is a fundamental branch of theoretical physics which replaces the classical mechanics and classical electromagnetic theory, because it is dealing with the particles at the subatomic levels. Okay, so quantum computer is a machine that is able to perform calculation based on the laws of the quantum mechanics, which is nothing but the behavior study of particles at the subatomic level. Okay. We know very well that, as we discussed earlier, classical computers will store electric signals as the data. Quantum computers will store the spin of an electrons as or the polarization of photons as the information over here. Okay. So what is the need? So there is a necessity, revolutionary stuff that is required, that we need to enable several novel algorithms and several information processing systems so that it is able to help you in solving some problems that a high performance computing domain can help engineers. Uh, I think my slide is not. Yeah. So now, I think I have given a small gist about what is a quantum computer, what is meant by quantum computing for the beginners. So now we are moving on to the essence of today's lecture, today's talk. Okay, so what is cryptography? We know very well that cryptography is the process of securing the information by covering the information through some mechanism, so that only the authorized party is able to read the information. Any other person who is able to access the information, he should not understand the information. So in all, what are the things that we use here? We use some mathematical techniques to ensure the integrity, authenticity and confidentiality of our information transfer. Okay, so the usual mechanism is we have a plain text that will be usually encrypted using an encryption algorithm. That plain text will be converted to a ciphertext, and that will be transmitted through the common channel to the receiver. The receiver will apply the decryption algorithm and he will get the plain text. This key, how will they transmit between this sender and the receiver? They will have a secure channel to transmit the key. Okay, so key will be transferred separately, ciphertext will be transferred separately. So this is how the basic cryptography mechanism will work. We are now focusing on public key cryptography. So public key cryptography is one of the backbones in securing this internet communication nowadays. Okay, so imagine that Alice and Bob, they have to communicate between them. How do they communicate in public key? By using public key cryptography. So Alice will send her public key to Bob, okay, and later she will send the information that is encrypted to Bob also. Okay, so what will Bob do? Bob will use the Alice public key to encrypt the message, and he'll send the encoded message. Here comes two key here, the public key and the private key. Public key is what Alice sends to Bob. Okay, anyone who is having this public key is able to open the information, but only if he wants to access the information. The private key, if he has only, he is able to access the information. Without having both the keys, accessing of the information is not at all possible. Maybe he can open the padlock, but he'll not understand what is the information that they are transferring between them. So that is very important that we have to think over here. So Alice uses her private key, and in the third stage, which has not been shared with anyone, and then she confirms the decrypted messages from Bob. So unless an eavesdropper who is having the knowledge of the private key, he cannot read any of the messages. So some of this techniques that is incorporating this public key cryptography over internet is this algorithms that you all know. I have listed these algorithms: securing email and messaging, digital signatures, and VPNs. They are all relying on public key cryptography. Okay. So everything is going fine. So what is the need of, okay, we invent quantum computers, that is all fine, no problem. What is the threat that this quantum is giving you for classical computers? So if we name the powerful classical cryptographic algorithms, one powerful classical cryptographic algorithm is RSA, and the other one is maybe ECC. Okay. So if the quantum computer comes into real existence, what will happen? So this is called as the quantum threat. Okay, so quantum algorithms is changing the balance here because of two powerful algorithms that has been found by two eminent scientists. Okay, so one algorithm is called Shor's algorithm. It is published in the year 1994. Okay, Shor stated that factorization of the numbers, factorization of integers is, and he is able to solve this discrete logarithm problems also in a polynomial time using quantum machine. Okay, he proved that this quantum algorithm will efficiently factorize any integers, even large integers. Also, it is efficient in finding out this discrete logarithm, which will effectively break the mechanism or the backbone of the highly believed secured algorithm called RSA. Okay, and the next one is Grover's algorithm. He is one more eminent person, Grover, who targets the brute force search. Okay, he gave a quadratic speed up algorithm to find in solving a searching problem in an unstructured database also. Even if you search in an unstructured database using this algorithm, you can effectively search your data in a very minimal time, probably in a complexity of the big complexity of root n. Okay, it's just half, cutting off the security into half. So when Groover algorithm is not actually breaking the functions of hash functions like AES and SHA algorithm by speeding up, they are just cutting their security into its half of its terms. Okay, so let us learn about what is Shor's algorithm and what is Grover's algorithm. As I told you earlier, Shor's algorithm is proposed by Peter Shor in the year of 1994. It is a quantum algorithm that is efficiently able to solve the problems that are considered as very hard for classical computers. Those two problems are integer factorization, and the other one is discrete logarithm problem. Integer factorization is, the job is like finding the prime factors of a large number. For example, imagine that I'm giving you a problem, that I'm giving you a number, like a small number, maybe 15. I'm telling you to find the factors of 15. Very easily you will find 3 and 5, or the factors of 15. Imagine I'm giving you a very large prime number, very large number, like very large number. How is it possible for you to find the factors? If you give the classical computer, the two factors 3 and 5, multiply it and give the result, it will give. If you give a very large number to multiply, it will multiply and give. But the classical computers will struggle if you ask it to find the prime factors. Okay. Also, solving this exponents in modular arithmetic, classical computers will struggle. Okay. So, in the classical computer, these problems will take an exponential time as the numbers are getting very large. So, on a quantum computer, if you run Shor's algorithm, will help you to solve these problems in a polynomial time. Okay, but whereas the classical computers will take an exponential time, Shor's algorithm will take only polynomial time. So I am showing you the algorithm, gist of the algorithm, how it is using a period finding algorithm to factor numbers. The step one is like you pick a random number, any random number. Okay, you compute the GCD of the random number, which is less than n, which is less than your assumed number. N is your number that is to be factored. If this GCD is greater than 1, it is that already you have found the factor. If it is not, you have to find the period. How will you find the period? Period is f of x is equal to a power x mod n. Okay, so this is hard for the classical computers, but this is very easy for the quantum computers by using the technique called quantum Fourier transform. And then it will come to a conclusion. It will find the value of r. So if r is even, it will find the values GCD of a power r by 2 minus 1 comma n and GCD of a power r by 2 plus 1 comma n. So if my value of number is n is equal to 15, it will take any random value of a and it will find the value of the factors of this 15 as 3 and 5 in an efficient way. This is what I have shown an example. So I am taking the value of n is equal to 15. I am picking any random value for a which is less than n. So a is equal to 2. It is assumed here. Now we are computing this period finding this period function. Okay. So f of x is equal to a power x mod n. So 2 power x mod n. Now our job is to find what is the value of r. So we now find r is equal to 4 because at this point we find the trivial solution. This 1 mod we are getting to power 4 is equal to 16, which is 1 mod 15. Okay. So since r is even, we can compute GCD. So GCD of r 2 power r by 2 minus 1 comma 15 will be GCD of 3 comma 15, and incrementing this 2 power r by 2 plus 1 comma 15 will be GCD of 5 comma 15, which will give you the factors of 15, that is 3 and 5. This is, I have shown you a very small numerical example. If you apply the same methodology for any large prime numbers, this methodology would work in a polynomial time, but the classical computers will take an exponential time. Okay. So why does this Shor's algorithm is threatening cryptography? So we believe that RSA, Diffie-Hellman key exchange and elliptic curve cryptography are on several powerful cryptographic algorithms that are securing our information in classical computers. Okay. So RSA is the security because it's we believe that it is highly secure because factoring of a large integers, maybe 2048-bit numbers and all, it's very difficult. But if Shor's algorithm comes into picture, it will break RSA completely. And then Diffie-Hellman key exchange, it relies on the hardness of discrete logarithm problem in modular arithmetic. Shor's algorithm breaks that too. So, which means that RSA and Diffie-Hellman key exchange would not be a sufficient candidate for if the person with the quantum computer is going to hack your information from the classical computer. And the other one is elliptic curve cryptography. Here this security is depending on elliptic curve discrete problem, which is again discrete logarithm problem. This is also easily breakable by the Shor's algorithm. So it makes ECC also unsafe when we are moving into the quantum era. And the next one is a beautiful algorithm, Grover's algorithm. So Grover's algorithm is very simple. It's a simple four-step algorithm. Okay. Here we are going to create uniform superposition of all input qubits, and then we will apply an oracle. So Grover's algorithm, the main objective of Grover's algorithm is to apply on searching problem. If you have an unstructured database and if you have to search a number from this unstructured database, using Grover's algorithm will efficiently search the target number in root n number of times. Okay, but whereas your other classic systems will take a more number of time. So how does this work? Grover's algorithm first creates a superposition of input qubits by applying Hadamard gate. Okay, over the initial qubits we start from the state 0. Over n qubits you can assume, no issues. The second stage is having an oracle. Oracle is a quantum subroutine that will help you to mark the correct solution. How it will mark? For example, in the unstructured database, I need to find the number 128. This oracle will be applied, and in the unstructured database, whenever your oracle is finding this 128, it will flip its amplitude sign, so that if 128 is my target number, so the amplitude is alone flipped for 128, all other numbers are remaining the same. So once it is flipped, we believe that it is the correct solution, and then we amplify the input. We amplify this flipped information, amplify this amplitude by applying this Grover diffusion operator. So the flipped amplitude information is alone amplified. Okay, so it is becoming a huge number, and all other numbers are becoming very low in terms of its amplitude. So it is highly helping you to differentiate other numbers from the target number. So the target number will have a very huge amplitude when compared with the other numbers. So it is just like applying a bias on your target. So this number of iteration has to repeat for step 2 and 3 and root n number of times until you find your correct target. Okay. So how does Grover search algorithm is becoming a threat? So Grover's algorithm is becoming a threat because of its quadratic speedup. Grover's the main attack that is considered in all the cryptographic algorithms is brute force attack. So Grover's algorithm is going to help the brute force attackers by reducing the number of search to the half. Okay, it is not making your entire classical algorithms like hashing algorithms, symmetric ciphers and all, it is not going to break, but it is going to weaken the strength of the algorithm. It is very important that you should consider. So if you wanted to completely make an environment that is completely quantum safe, Grover's and Shor's algorithm is often an efficient candidate for breaking all your classical cryptographic algorithms. So what do we do now? So these are all some of the highly believed algorithms that are considered to be very efficient in classical computers. So RSA, Diffie-Hellman key exchange, digital signature, AES, SHA, everything, they are weakened or fully broken by Shor's and Grovers. So imagine our future, what will we do if they are broken or if they are weakened? So definitely we need to move towards the quantum era. There is no choice. It is a necessity that we need to move to secure our own data. So before going into what is post-quantum cryptography, let us know what is quantum cryptography. Quantum cryptography is a method of securing information, securing the communication process using the principle of quantum mechanics. So here, imagine this is a model how the quantum key distribution is going to work. This figure is illustrating you. Imagine we have a sender and receiver. So the communication through quantum cryptography happens with the help of the photons. The polarization angle of photons is going to tell you the information. So the polarization angles can be 90 degree, 180 degree, 45 degree, and minus 40. It is inverse. Also, in measurement side, we can apply these basis vectors. These basis vectors can be vertical basis vectors, also horizontal basis vectors. So if the sender is sending an information in this polarization mechanism and receiver basis vectors are applying these particular, see I have 90 degree polarized information. I am applying the basis vector over here. They both resemble the same, so my receiver information is measured. Here I am receiving I am applying a horizontal basis vector, so I am getting an information. Here I am getting an information. So what are the information that the public discussion shared secret key will take out of it? So here the sender polarization and the receiver measurements are matching. I will consider this. The center polarization and the receiver measurements, they don't match over here, so here the information is null. I don't have any valid information over here. It gets mutually cancelled with each other. I don't get any information. Only if there is some mutual match between sender's polarization and receiver measurement, we could retrieve the shared secret key. Similarly, for the third thing, we have the matching between the sender polarization and receiver measurement. We receive the secret key. And over for the last bit of the polarization also. All other things we don't receive. So imagine the drawbacks of this quantum cryptography. Quantum cryptography depends on the hardware of quantum, like photonic hardwares, which needs photon detectors, quantum channels, which is definitely costly and complex in physical deployment implementation. And also, when we rely on photonics communication, the communication range is very low, very limited range of communication, because quantum signals may degrade over long distances. And imagine how many number of quantum repeaters that you have to enable if you are increasing the communication range, because the quantum information does not allow this cloning of information. So it is there is a theory called no cloning theorem, which tells you that quantum informations cannot be exactly copied, or it cannot be cloned. So even you have quantum repeaters, this cloning theorem will not support you to copy the exact states. So which is again a very complex stuff to implement over large scale of communication, and this is again an expensive, and also right now it is quite impractical for large scale adoption. For large scale, we know that recently India has demonstrated this quantum secure communication. The professor of IIT Delhi and DRDO, they also did for a very short range communication. So implementation cost, setting up this and maintaining this environment is actually highly expensive, and also it becomes impractical for large scale right now. And now comes, as I stated you the drawbacks of quantum cryptography, I would like you to tell quantum cryptography, the importance of post-quantum cryptography. Uh, okay, so imagine that everyone are having quantum computers at home. We come to an era like that. But still, we have to maintain some records. We cannot completely move from the classical computer to quantum computer just like that. We have some data that is to be maintained in a secured way. Okay, so that even if the person who is trying to eavesdrop your information, if the person who is trying to hack your information through a classical computer, he should not able to, if he tries to target your classical computer, he should not able to access your information. Imagine a scenario, Alice and Bob are communicating between each other. Alice is having a classical computer, Bob is also having a high performance computer. They both are classical computers. Imagine a hacker is trying to eavesdrop the information between these two people, between these two persons. The hacker is having a quantum computer. What is the scenario here? Okay. The scenario is like quantum computer is highly efficient. It can easily eavesdrop the information. So what we have to do in order to make our current classical systems vulnerable to quantum attacks? So traditional cryptography is vulnerable to quantum attacks because of the invention of Grover's and Shor's algorithm. So PQZ is a valid candidate which is helping you to adopt the classical computers resistant against the vulnerable quantum attacks. Okay, so PQZ refers to the cryptographic algorithms that is designed to remain secure against attacks for both classical and the quantum computers. Okay, so quantum computers will not completely replace the classical computers right now. So the need for the post-quantum cryptography arises in order to ensure secure communication and data protection in the hybrid computing environment where both classical system and the quantum system is coexisting. All right. Right. So what is the need for post-quantum cryptography? So as I told you earlier, we need to protect our data that is available in the classical computers against quantum threat. So protection against quantum threat. Quantum computers can break widely used cryptographic algorithms, RSA and ECC, by using shards. And also there is a concept called harvest now and decrypt later. This is a very big threat. Advisories may collect all your encrypted data now. Maybe after several years, they may try to decrypt later when quantum computers become more powerful. So in those cases, PQC will safeguard your sensitive information from future attempts of decryption. And the critical data like financial transactions, healthcare records, and government communications often needs to remain for more decades. Decades of information, we should keep it secure. Okay, defense information. So Post-quantum cryptography will help you to provide robust protection of long-term data storage and transmission. Also, uh, post-quantum cryptography supports crypto agility because it helps you to because we need to transit from classical cryptography to PQC because it takes time to completely replace all the cryptographic algorithms that is existing in the current classical computers. So, early adoption will allow the organizations to prepare and adopt without risking the security. Okay, there is no choice. We have to definitely secure our information, so we need to make a transit to PQC indeed, definitely. So, imagine in 2024, the market of post-quantum cryptography was around $302.5 million. The post-quantum cryptography market size is estimated to grow from $302.5 million to $1.88 billion by 2029 at a compound annual growth rate of 44.2% during the forecast period. In just 5 years, it is expected. Okay, the market is very highly demanding market. Also, I would like to give the statement of CEO of Google, what he said. He said that we are also taking steps to develop quantum computing responsibly given its powerful potential. Our partnerships with governments and the security community are helping to create systems that can protect internet traffic from future quantum computer attacks. And we are making sure services like Google Cloud, Android and Chrome remain safe and secure in a quantum future. So it all obviously says that we definitely need the necessity of moving from classical cryptographic algorithms to post-quantum cryptographic algorithms to secure our information in the upcoming quantum future. Okay. So, keeping all this in mind, National Institute of Standards and Technology, in short it is called as NIST, it plays a significant role in establishing standards and guidelines for cryptographic algorithms, ensuring the security of digital communications and data. So, what it did? In 2016, NIST predicted the importance of PQC and it announced for a PQC standardization process. In 2017, it received around 82 submissions. Okay, so for standardization process, several people proposed their algorithms. Out of 82 submissions, 69 candidates stood out in the first round, and in 2019, second round happened. So out of the 69 candidates, 26 candidates moved to second round, and in 2020, 15 algorithms moved to third round, and in 2022 to 23, they released a draft standard for public review, and in 2024 they released the final standard. So let us see them one by one. So in 2024, a draft was released by NIST for the first three finalist standard for post-quantum cryptography, making a significant milestone in the development of encryption methods against quantum computer attacks. The standards of FIPS 203, 204 and 205. So 203 is based on the module lattice-based key encapsulation mechanism. It is called the Kyber algorithm. Okay. And 204 is dilithium algorithm. It is also based on lattice-based signature. And 205 is it's based on hash-based digital signature algorithm. It is called as Phoenix Plus algorithm. Alright, so basically NIST released 5 categories of post-quantum cryptographic algorithms. The 5 categories, the first category is lattice-based cryptography, code-based cryptography, multivariate quadratic cryptography, hash-based cryptography, isogeny-based cryptography. While NIST officially classifies them based on their functionality as their key encapsulation mechanism or having digital signatures in their mind. So these categories are made based on the key encapsulation mechanisms and digital signatures. I'll deal one by one how does it work. The mathematical descriptions I'm not giving right now. I'm just telling you because some of these algorithms are broken. Only 3 are surviving now. Among the 3, I'll tell you how this lattice based is around working. So lattice-based post-quantum cryptography. Lattice-based post-quantum cryptography refers to the cryptographic systems that relies on the hardness of solving these lattice problems, which are believed to be resistant by quantum computers. We know what is a lattice. Lattice in the context of cryptography is a discrete mathematical structure consisting of infinite points arranged in a regular and periodic pattern. Here I have shown you two different lattice structures. It is shown in 2 dimensions. The first figure is shown in 2 dimensions. The second figure is shown in 3 dimensions. Okay, so it is defined a set of basis vectors that span over a space. So the linear combination of these vectors will generate all the lattice points. While creating the lattice points, we have to consider whether the lattice points are created on a good basis or on a bad basis. Good bases are usually short and near orthogonal vectors, which will help decoding efficient, and bad basis vectors are long skew vectors. Long skewed vectors, if you consider for basis, it will obviously will make very easy for decoding. So good basis vectors and bad basis vectors that use short orthogonal vectors, and bad basis are long skewed vectors. How does it work? I'll show you. Imagine that Alice and Bob has to transmit their information through lattice. So key generation is like they are going to create the lattice and they are going to select their basis vectors. Okay, Alice selects the private key, which is usually a good basis vector, which is short and well structured, and then she generates a public key. Public key is always a bad basis vector with long and skewed vectors, because long and skewed vectors, they are very difficult to solve. They are very difficult to decrypt. So private key is always good basis vector and public key is always the bad basis vector. What does Bob do? Bob encodes his message as a lattice point using Alice public key. He adds some small random noise to the message to make it resistant to attack, to make it resistant towards any attacks, and then he sends an encrypted message to Alice. Since Alice is having the private key in good basis, she can efficiently remove the noise and recover the original message. But an attacker, if he has the public key, even if he has the public key, he will struggle, because he cannot decrypt where is the message is actually available over the lattice, because lattice position finding, lattice vector finding is one of the hardest problems. It's the hard lattice problems are very difficult to solve. So this property makes lattice based cryptography is one of the best and leading candidates for post cryptography. So these two algorithms, Kyber and dilithium algorithm, is surviving till now. So this hard lattice problems are not very easy to solve even with a quantum computer. Okay. So code-based cryptography is a type of cryptography that uses error-correcting codes to protect your information, like how we use Huffman code to protect our information. So it is hiding, it's a process of hiding an information with error, and only the person with the known error is able to fix the errors, and he can read the original image, even in a noisy communication channel. So I'll tell you a scenario to imagine this scene. Imagine a student wants to pass a secret message to his or her best friend. He wanted not to share this information to any other person, especially the teacher or the other students. So what he'll do, he'll write the message, he'll scramble the message in a very efficient way so that only his friend will know how to unscramble it and understand. The same way, so private key and public key are generated by Alice. So special code will help you to fix the broken message, and the scrambled version of the special key that anyone else other than Alice and Bob is unable to understand. So Bob wants to send a message to Alice. He uses the public key that is generated by Alice, and hence he sends a scrambled message to Alice. And as they both are aware of how to fix the errors, they can efficiently ignore the errors, and then they can read this information. Okay, so anyone with a public key can read the information, but they cannot exactly decode what is actually done. Okay, imagine if the teacher comes and picks the paper from the student through which the information is passing. She can see what is there, but she cannot unscramble the information, and she cannot learn, and she cannot decode the information. So this is the concept here actually. The multivariate quadratic cryptography is a type of post-quantum cryptography that secures the data using mathematical problems. Okay, so solving many quadratic equations with multiple variables. Here the same thing. Consider Alice is wanted to transmit the information. She is constructing a math maze using some equation. Okay, Bob is sending a secret. So he uses, and after she is building the maze, she just creates the mathematical equations and she's creating a maze, and then she is scrambling the information. Bob wants, in the other word, Bob wants to send a secret message hello. So what he does is he uses scrambled maze of Alice, and then he sends the messages inside the math puzzle. He sends the puzzle to Alice. So Alice can use a secret map, that is a private key, and then she can very easily solve the maze so that she finds the original message later. Okay, so that is what here. Isogeny based cryptography is actually isogeny means that the mathematical mapping between two elliptic curves that is able to preserve their structure. I have shown two elliptic curves. So these two are isogenic curves because their mathematical structures are preserved. So isogeny based cryptography secures a communication by using isogenic paths between the elliptic curves instead of relying on big numbers like mathematical equation solving, linear equation solving using multiple variables or lattice. It is believed that the goal is to find the path between two curves. Between these two curves, they have to find the path so that only then they can decode the information. Okay, so this is believed as one of the hardest problems. And the next one is hash-based post-quantum cryptography. So hash-based post-quantum cryptography is a branch of cryptography that relies solely on cryptographic hash functions. Okay, so one such algorithm for hash function is Phoenix Plus. It is still surviving because it is able to provide strong security guarantee because they rely on number theoretic assumptions like RSA or elliptic cryptography, which are vulnerable to quantum attacks. So how it works, imagine that we have two business partners like Alice and Bob. They have two sealed boxes. One box says that we agree and the other says that we don't agree. Each of the boxes sealed with a secret code which is known only to them. In the decision process, Alice and Bob are individually choosing their box based on whether they agree on the contract or not. Okay, they send the code for their chosen box. So the code is like the private key, and the box that is having the content, whether you agree or we don't agree, is the public key. So how do they verify? Alice and Bob exchange the codes to open the boxes, so they ensure that their decisions are securely verified. This is how it is working. So now I'm giving a gist of this NIST post-quantum cryptography and their post-quantum cryptographic algorithms and their status now. So lattice-based cryptography, as I told you earlier, their example algorithms are Kyber and Dilithium. They are standardized and they are strong. Okay, they are making the efficient backbone of PQC. Hash-based algorithms, Phoenix Plus is still surviving and it is standardized. It is very secure and is one of the conservative fallback option for PQC. And the other one is code based. The classic Picalis algorithm is still considered, but it is not fully yet broken. Okay, so the multivariate quadratic and isogeny algorithms are broken in 2022. Rainbow algorithm is one of the one of the algorithm candidate for multivariate quadratic. It is broken in the year of 2022, and isogeny based algorithm is called Psych. It is also broken in 2022 by classical cryptanalysis techniques. I think we are running out of time. I would like to just give a small glimpse about what is a Kyber algorithm and I'll finish the session. So Kyber algorithm is a key encapsulation mechanism. It's based on the lattice post-quantum cryptography. It's one of the secure way to communicate between two parties. Okay, so here the method is like the first step is to generate your public key and private key, and then the Alice will use an encapsulation mechanism. Bob will use the encapsulation mechanism. He'll generate the information and encrypt the information to the ciphertext, and he'll send the ciphertext to Alice, and decapsulation mechanism will be handled by Alice. She will use a private key to decrypt the ciphertext. This is actually the gist of the algorithm I'm giving you. And mathematically, if you have to say, key generation is the process of is a process as shown below. So a public matrix is available, the secret vector. So encapsulation scheme is done by Bob. He is going to use hash function to create his secret message and the ciphertext. Decapsulation will be done over the secret message and the ciphertext, and Alice will be able to efficiently decrypt the information. Okay, so by applying the hash function at last, and this is one of the successful algorithms that has been still available in post-quantum cryptography schemes. Okay. I think now if there are any questions, I would like to address the questions, and thank you for the opportunity.
Yeah, thank you, ma'am. Thank you so much for the wonderful presentation. So, shall I have some
Thank
questions
you.
from the participants?
Yeah.
Okay. Actually, first question, how can post-quantum cryptographic algorithms be seamlessly integrated into existing digital infrastructures without disturbing current security systems?
Yeah, every right now every industry is focusing on these kind of techniques. That is why we are making the systems reliable. No, so classical cryptographic schemes, this is what actually what all these listed algorithms are working in they are made to seamlessly work with the classical techniques, and they are trying to enable whether it is possible or not. While trying these algorithms only, they found these algorithms are broken or not broken and all. Initially, they had so many algorithms in the list. So from 2016, there are seamless group of people, those who are working on this technique of integrating this classical cryptographic schemes, incorporating this post-quantum cryptography algorithms. By next, then they'll check whether they are able to withstand the Shor's and Grover's attack. Until then only they are able to find this lattice based Kyber and lithium. They are an efficient and suitable candidates. Okay, so you can refer these articles that I have listed here, so they can help you to understand in a very better way.
Yeah, thank you, ma'am. What role will artificial intelligence play in enhancing or challenging post-quantum cryptographic methods in the future?
In the future, AI. Okay. uh, So adoption of PQC and AI in cybersecurity is a very efficient cybersecurity paradigm actually. So as we are in the stand of threshold of the new era, so we have to determine evolution of PQC driven threats by the computers is a compromise for cryptographic algorithms like RSA and elliptic curve. So industry experts are right now in the full realization of the threat, and I think it is a very great research area to work out, and we need to find how come the large key sizes and adoption of post quantum is actually resistant against all this attacks and making a quantum enabled feature. Actually is a nice area of research which should be explored in depth.
Okay, thank you, ma'am. Okay, this is my final question. How can post-quantum cryptography ensure secure communication in rapidly growing fields like IoT, 6G networks, and autonomous systems?
Can you come again? How can PQC help
Yeah,
in?
yeah. Post-quantum cryptography ensures secure communication in rapidly
Okay,
growing fields like
okay.
IoT, 6G networks, and autonomous systems.
Yeah. So they we know that the classical computers, we believe that RSA and ECC are the efficient candidates, no? So it is believed that PQC will make our future communication secured by protecting the key exchange and encryption, by ensuring long-term confidentiality, and we need to focus on working how come the existing communication protocols are compatible with this PQC. We need to check everything out. Okay, they are all when we have to enable the complete quantum safe digital communication. Right now we are in the initial infancy state. We have just demonstrated, India has just demonstrated this communication of very small communication, quantum secure communication that has been actually carried out. So it is existing communication systems can have a transition from classical computing systems to a quantum computing systems without redesigning. That is what everything. We need not do everything right now from scratch. This post-quantum cryptographic algorithms implementation will help you to solve this kind of problem. So industries are actually working on it, and Once it is completely enabled, PQC standards will help you to work with protocols like VPNs, email encryption techniques, so that we need not build everything right from scratch to enable the computing systems or the devices that are available right now. Once we are completely moving to a quantum era, then there is a scenario like we need to build everything right from scratch. But right now, with the help of PQC, it is not necessary that you have to start everything from scratch. You can just augment your device with the help of PQC by enabling this scheme to work in a better way against quantum threats.
Yeah, thank you, ma'am. Thank you for the useful answers. They have been really helpful in clarifying the topic. I hope
Yes,
the
thank you.
participants were able to follow along and understand the key points shared. Your insights have certainly added value to the session. So, on behalf of everyone present here, I extend my heartfelt gratitude to Dr. S.S. Gayathri for taking the time to join us today and for delivering such an insightful and thought provoking session. Your deep knowledge of quantum computing and cryptography has not only enriched our understanding but has also sparked new curiosity and inspiration among us. Your ability to simplify the complex ideas like quantum circuit design and post quantum security and connect them to real world applications has been truly commendable. The passion you bring to both teaching and research is evident and it has left a lasting impression on all of us. So, we are fortunate to have learned from your expertise and experience, and your words will surely motivate us to explore this fascinating field with greater enthusiasm. So, once again, thank you, Dr. Gayathri, for gracing us with your presence and wisdom. We look forward to many more opportunities to learn from you in the future. So, as we take the insights from today's session forward, we carry with us your encouragement and a vision to keep innovating and thinking again in this exciting era of quantum technology. So, thank you, ma'am. Thank you so much.
Thank you. Thank you for the opportunity. Thank you.
Yeah, thank you, ma'am. So, definitely we will meet in future collaborations also.
Thank you. Thank you.
Thank you, ma'am. Yeah.
How will you be sending any pictures of this is and the feedback of this
Sure,
session?
sure. We will send the certification and memento and the video link, okay?
Okay, thank
Sure,
you.
ma'am. Thank you, ma'am. Take care. Bye bye.
Right, thank
Yeah.
you. Hope the session was indeed useful. Thank you.
Yeah, thank you.